Starting event. All right, I think we are live from the Oxford University Museum of Natural History. Welcome everyone in the chat. And people are keep coming in. All right, so welcome to the second session of the 64th annual meeting of the Palaeontological Association. This session will be based on 5 flash talks of 5 minutes each, and we will have a questions and answers session at the end of it. Should you have any connection issues, please click on the reconnect button at the top of your screens, and please use the chat to ask questions as the talk goes along. Mark your questions as such using the red circles at the right of what you're typing, and we'll try to select some of the questions for the speakers for the final session of this for this final part of the session. All right, next speaker is Hue Li.
Hi.
Hi. How are you doing?
Good. Okay. So.
All right, I will now stop this and start your presentation. All yours. Thanks.
Okay. So hi, I'm Hue. I'm currently at the University of Hong Kong. I used to be in Imperial College London and the Natural History Museum. So today I'll be talking about my project on anatomical organization and modularity in the skull of archosaurs, which has been published in late September this year. Okay. So the evolution and diversification of the skull of archosaurs have been associated with the changes in the patterns of phenotypic integration and modularity. My project focuses on one type of modularity called organizational modularity, which is on how the cranial structure is formed based on the interactions or relations among different anatomical parts. So in this case, it's the physical arrangement of cranial bones. So to quantify the structure, imagine that cranial bones are like points in a network, and their articulations are links between these points. So once you think of a skull as a network, it's easier to quantify how the cranial structure evolved through the use of several network measuring variables. So we use principal component analysis to find variables that are most likely to explain the variation in cranial structure among archosaurs. And we include modern birds, non-avian dinosaurs, and pseudoscians. So Palmanova showed that modern birds are significantly different from pseudoscians and non-avian dinosaurs, but there is no significant difference between pseudoscians and non-avian dinosaurs. It means that the pseudoscians, such as alligator, and the Saurischian raptor are biologically similar. So for example, despite the orbits are circular in dorsal view for alligator here, and circular in the lateral view for raptor, they are surrounded by the similar elements, such as the lacrimodes, the frontals, jugos, postorbitals, and frontals. So besides adult birds, we also include some juvenile birds and show that their ontogenetic trajectories to their adult forms as those orange arrows. So we found that the juvenile birds tend to have a topology closer to non-avian dinosaurs and pseudoscians than their adult forms, in terms of the density of the connections and the number of cranial bones. So as an example, I labeled the juvenile medium ground finch as 1 and its adult form as 2. So you can see from the images above my head that some cranial sutures are present in the juvenile, such as the frontal parietal sutures. And these sutures are fused in the adult forms. So in contrast, the juvenile alligator has a bone arrangement that is similar to its adult form, and it appears to overlap in the morphospace. This is because that most alligator sutures are remain open from the postnatal stages to the adulthood. So thank you for listening.
Thank you so much, Hue. And Anne, are you there? All right, so Anne de Celis, the slides are upcoming right now for you. And the stage is yours. Thank you.
Thank you. Hi, hello everyone. So I'm going to talk a little bit about the shape changes that occur in the crocodilian palate during the ontogenetic process. So in previous works, those were centered around the dorsal area of the skull, and in the few works that contained the palate, just some species were analyzed. It is also important to note that the palate is a key structure to interpret the evolutionary history of crocodilomorphs, and thus our objective in this work was to identify the patterns of shape change related to ontogeny in all extant crocodilian species. To do so, we took photographs from 334 skulls from all species, and the specimens ranged from juvenile to adults. We chose to do a two-dimensional geometric morphometric approach, and to do so, we constructed a new landmark configuration that you can see on the right, and consists of 20 landmarks. We did several principal component analysis and regressions of shape versus the logarithm of the centroid size to inspect those patterns of ontogenetic patterns. So here you have the PCAs. At the top left, you have the first principal component versus the second one, and right below it, you have the second principal component versus the third. At the top right, you have the shape changes that occur along each one of those principal components. And the color legend refers to the three main crocodilian lineages. Whoops. It is also important to note that the size of each symbol represents the logarithm of the centroid size. That is, juveniles will have a smaller symbol rather in comparison to adults. And you have an example at the bottom left. So first, if we observe the PCAs, we can see that each lineage occupies a different morphospace. Especially this segregation occurs along the second principal component, which represents the different shape of the suborbital fenestra and the width of the anterior part of the snout. And it is also interesting to note that juveniles from different lineages do not overlap their shape in these PCAs, which means that their shape is very well established in each lineage from this early stage. Second, all our regressions of shape versus the logarithm of the centroid size were significant, which means that the shape of the palate of these animals substantially changes from juvenile to adult specimens. And having in account the results from these regressions, in which we had the shape of the first, second, or third principal components versus the centroid size, we had several results. Here is one of them. And we observed that the first principal component is related to interspecific variability rather than ontogeny. And this first principal component basically represents the length and width of the snout. And there were just a few sections, in which were alligatorians, tomistoma, and gavialis, in which we observed that from juvenile to adult specimens, there was a great change of those dimensions of the snout. And also we observed that during the ontogeny, their shape moves towards positive values of the second principal component and negative values of the third principal component. This increase in the second principal component was especially important in crocodilians. You have an example here with the Nile crocodile. And the second principal component represents basically, as I said, the shape of the suborbital fenestra, the anterior width of the snout. And the third principal component represents that we can observe that juveniles located on the right of the third principal component to the left, where are all the adults, we observe that the palatines are posteriorly displaced during this process. So our next step is to include the ontogenetic series from the fossil record of Eusuchia. And well, that was all. Thank you for your attention.
Thanks so much, Anne, for your talk. And greetings to your cat or doggy as well. So, and at this point, please, I will call all the presenters / talkers to turn their cameras on, and we'll have a bit of a discussion while addressing some of the questions that have been popping up in the chat. I think we have most of us there are in them. Are you around? Perfect. All right. Yeah. All of us are here. Hi, guys. Good to see you all. So we might actually repeat some of the questions that have been already addressed in the chat, and not everyone follows the chat. So please forgive me if you feel that you are repeating yourselves on that front. Some of the questions out there, I have here one for random on the size of your data set. I know that you've just typed about it, but would you mind addressing that here, please?
Yeah, sure. So it's around 400 species with 8 variables, including the basic length and width, and then you have other statistical metrics on that. And color is obviously the thing that's being predicted. So that's the other one.
Nice. So one of the attendees noted that you were only using measurements, right? Length, width. Have you also considered using raw images like SEM? We might be very data rich.
Yeah. So with the SEM, the problem is that most fossils are not, these melanosomes don't really appear absolutely geometrically regular. And taphonomy is also a big thing. So sometimes these melanosomes coalesce into shapes that you can't really identify, and you have to kind of use your own judgment to actually measure them and then use that as input data. So yeah, it has come to my attention, but it's not as easy to implement that.
All right, thank you. A question for Natalia. Would you mind please discussing about the taphonomy of the deposit of your fossil? Any thoughts on why it's preserved in 3D?
Okay, yeah, I answered in the chat, but I can answer also here. I have no idea. I would love to know why it's actually like this. It's an anomaly. We don't see that kind of preservation in pterosaurs at all, because pterosaurs usually become flattened. Their bones, even my pterosaur bones, are millimeters. Bone walls are just millimeters thick, so they usually collapse. And with our pterosaur, one side, the left side, is fully preserved in 3 dimensions. The left one becomes squished and very deformed, and that doesn't make any sense because you have sort of very localized flattening. I think it might be just fluke of the preservation in that area, because we don't have any other animals preserved to that completeness in those dimensions in all of the great Inchtherian group from Middle Jurassic of Sky. But it deserves more chemical and of analysis to actually understand why it had happened. But it's great because pterosaurs, especially beast pterosaurs, rarely get preserved in 3 dimensions, so that anomaly actually helps us a lot when coming to understanding this kind of animals. So it's a happy anomaly. I hope that answers it.
All right, thank you. I have a question here for Sophia. How big are the teeth that you're hoping to sample microware from? And are you planning to apply 2D or 3D analysis?
Yes, so I think we're just initially considering to put. We're going to use OP style, so orientated patch count rotated. Should answer the other question first. The animals themselves, the skull's about 2 to 3 centimeters long. The teeth are fairly small, but also fairly big, because these animals actually only have like about 4 large teeth in the skull. So I don't know, maybe.
We have, all right. So we have some technical issues there. It's quite appropriate, right, to leave the room when being asked. Well, of course, this is a technical issue. And we'll move on to the next question. And one for Anne. What do you hypothesize is behind the change in morphology? A change in diet as crocs get bigger?
Yes, I think that's the reason behind it, because as they go bigger, their muscles go through, you know, the suborbital fenestra. They get bigger and they need more area to attach. And yeah, so I think that's right, the reason behind.
Nice, thanks. And sorry, Sophia, we
Sorry,
lost you there.
I don't know what happened. It just went down.
That's fine. That's fine. Technical issues will not prevent us from enjoying from your answer. So, would you mind please resuming?
Okay. So yeah, orientated patch count rotate can be used. It's unidimensional just to look at the surface complexity. There is another form. I'm trying to remember what it's called. A multi-proxy dental morphology analysis. The main issue about using this is it does consider like slope and steepness of the teeth. Is that there isn't really stand taxa to use for it yet, so we're mainly just looking at these this two-dimensional at the minute. We also plan to look at microwear, which I think is, we haven't actually gotten around to that bit yet. I think that's probably two-dimensional as well. Does that answer the question?
Yes, all right. Thank you so much for that, in spite of the technical difficulties. I would like to remind everyone to encourage everyone to keep sending questions to the Flash speakers. We will be likely in the Discord server, roaming around the rooms and enjoying with discussions with everyone. And I would like to thank all the speakers today for their amazing accuracy and the timing wise. It's very much appreciated, because we all know it's very difficult to cram everything in our research into 4 minutes. So we really appreciate it. And before ending the session, please remind you that keep using the links that you are sent in your email inbox to attend to the upcoming sessions. And right now in the Discord server, we are starting the first poster session. And remember that you can actually access the posters through by using the login in the annual meetings webpage, using the details that you have been sent as well. And so that's happening right now in Discord server for about an hour, and then we have hopefully some time to get some lunch. And remember that the next talk session will be in about 2 hours at 1:15 London time, and those will be 15-minute talks, and there will be 2 parallel sessions. And I think that's all from our end. I hope you enjoyed the talk so far, and see you soon. Thanks to all the speakers again.
Thank you so much.
Bye, thank you.
Thanks for having us. Merry Christmas.
Merry Christmas.